So good morning once again. And so to get, let's get few things clarified. First of all, you don't need any programming experience. Any kind of background is not assumed for this course. Okay, we will start from fundamentals and slowly build up on the fundamentals. Some of you may have prior experience with programming, and some of you may not have any experience at all. But by the end of this course, all of you will be more or less be at the same stage. The first couple of weeks, some students may look more proficient, and some may be trying to get a grasp of the ideas. But that's all fine, perfectly fine. So don't compare yourselves with your friends. Your goal is not 1 week or 2 weeks or 3 weeks. We will achieve the course learning objectives as we progress through the course, and by the end of the course, we will be proficient enough to write reasonably complex programs. So yes, nothing to worry at all. And the textbook for this course, I will share the screen. So this is the textbook for the course, K.N. King, C Programming, a Modern Approach. This book is a bit expensive, but it's a really good book to have. You can try to get a e-copy also, but I would suggest getting a hard copy of the book. And if any one of you have questions, please raise your hands, or you can type it in the chat box. I keep checking the chat box as the class progresses. So feel free to talk in the chat box. Okay, this is the only book that is required. And so please keep checking your institute email. In a week or so, we will set up we will set up a alternate portal. There is this portal called as elearn.triple-IT.ac.in. So this is the place where all the course content will be posted. All the video lectures, etc., will be posted on this site. So this book will be, there's this question, will this book be used only for the first semester? Well, I mean, all these books, it's a learning is continuous. So you will use it predominantly in your first semester, but it will be useful in subsequent semesters too. So let's get started. Anyone would like to ask anything? You're all excited for the course? I hope you're all excited for the course. You are able to see the screen? Raise your hand, then I will unmute you. So there is, okay, so a couple of, you asked about me. So my name is Suresh Purini. I have been in Triple IT for more than a decade. I'm a faculty member here. I belong to computer systems group. My areas of research are, I work in compilers, distributed systems, computer architecture. I have a wide variety of research interests. And yeah, so that's all about me. I like to play. I like to do yoga. I like to meditate. And yes, and I would like to teach and be with my students, work with them. And that's all about me. What do I play? I play, at a gully level, at street level, I pretty much play most of the games: soccer, cricket, table tennis, hockey. So most games I play. Volleyball, but not like any player, but I can play all right. Why are we beginning with C? Why not C++, Java, Python? Good question. So there is this question. So why are we starting with C? Why not C++, Java, or Python, etc.? What happens is, in the C programming language, you will understand these ideas slowly, because some of you may not be quite familiar with the programming language concepts. The language features or the language abstractions provided by the C programming language, they are simple and yet powerful. And because of their simplicity, we will be able to see how these language features are mapped into underlying system, how these language features, they map to how they will be translated into a form which your computer, which your processor or which your computer can understand. And yet it is very powerful. That is, you can write any program that you would like to using the C programming language. So as beginners, you're all going to be computer scientists. This understanding of mapping language abstractions to underlying machine, it is important. And when you use C++, Java, Python, etc., while you might be able to write programs, okay, and using approaches such as object-oriented design approaches, etc., the language features are complex that it's hard for you to see how they get mapped to the underlying system. So yeah, personally, I feel it's important. You are in your first semester, so learning C++ or Java, learning those features, we can learn by yourselves later on. But being able to see how a particular language feature gets mapped to the underlying system, it's important. Okay, because we want you to write new programs. You should be able to design new programming languages, not new programs. Of course, new programs you write. So you should, we want you to train in such a way so that you can design new programming languages, come up with novel language abstractions, etc. And for that, this base is very good. Which platform do you suggest for learning other languages once we get a grasp of C language? See, Python is something which all of you have to learn for sure because it's a power tool. You can do lots of stuff very quickly using Python. You learn Python anyways. And C++, Java, yeah, you can pick any of these languages. Anyways, so it's a good set of questions. So let's start. The objective of today's lecture is to understand what is underneath a computing system. What is there in a computing system? It's a 10,000 feet view of your computing system. Because you are going to write your programs on your computer and you are going to run them on your computer. So you need to know what constitutes your computing system. So if you take any computing system, so it consists of hardware and software. And if you look at the software, the Zoom software using which you are attending this lecture, it's an example of a software, your web browser. And so all these things, they are software applications which run on the hardware. Similarly, your mobile phone, it's also a very, very powerful computer. And yeah, you can run so many applications on your mobile phone. You end up playing lots of games, like on your mobile phone. So all those are applications which run on your mobile phone. And so this, if you look at this, your laptop or your desktop, it's usually when we say computer, that's what comes to our mind. And then a very powerful computer in your pocket, that is your mobile phone. So keep that in mind. And then most of the time you keep searching for, keep Googling, right? So again, what happens when you when you type in a query to ask Google something? What happens? What do you think happens after you give a search query to Google? You ask Google something, and then what happens? The query goes to Google servers. Nice. So excellent. Whether you a minute. Yeah. So whether you so this is your mobile phone or your laptop. Okay. So let's say this is your laptop, let's say. And when you give a query, then what happens is it goes to your Google Cloud or Google data center. Google has many data centers across the world. And Google, in each of these data centers, they contain tens of thousands of machines. Okay, so these are all machines. There are tens of thousands, maybe tens of thousands or even more, I don't know, machines. So your search query will be given to all these machines or some number of or some subset of machines, and all the results given by different so like, for example, this machine may say, hey, I found these results against AAAT. Let's say AAAT is the query that you gave. And then or AAAT CSE or ECE program, that could be your query. And different servers will give some results. And all these results will be merged and those results will be sent back to you. So here again, this idea, this is like a massive distributed computing system. And the hardware here is a collection of machines. Each of these machines, they could be just like your desktop machines, for example. But there is this nice software that runs on these machines, which does the search and merging of the results. Anyway, the point here is take any computing system, be it your laptop, your desktop, your mobile phone, or a distributed computing system such as a Google data center. There are two components to it. One is hardware and the other one is software. All right. You're all with me here so far? And if anyone has any hesitation in asking a question publicly, you can put a private message to me. Not an issue. Feel free. You're all with me? Good. Those of you who are not with me, you should put a message also, because I see 20 messages of yes, and I think it's all good and I proceed. But if there is a question, you should put great. There is a question on attendance. We'll get to attendance later. Not bothered about it right now. And if you take any computing system, again, laptop, desktop, mobile phone, for the time being, let's keep the distributed systems such as Google data center aside. We'll just focus on regular computing systems that we use on a day-to-day basis, which we see them. So any computing system, if you look at its hardware, it consists of three important components. One is processor or CPU. And the second one is, the second component is called as main memory, also called as random access memory, RAM. And the third is a bunch of IO devices, like, for example, your keyboard, display, webcam, microphone. All these things, they constitute IO devices. It doesn't matter which computing system we talk. Every computing system, if you look at the hardware, these are the primary components. A processor, which is also called as CPU, main memory, also called as random access memory, and a bunch of IO devices. So today, I will release one small survey or small homework where you have to fill in that form. What is the processor of your system, of your laptop? How much memory it has, and one or two other simple questions related to your computing system. So, as you are all entering IIIT, you would have done a lot of research on what laptop to buy. You would have read quite a bit about these things. Just to get a sample, can you tell what processor is there on your system? What processor is there? The computer which you are using now, what AMD Ryzen? I want to get a feel. Intel M1, i5, i7. Nice. More Intels I'm seeing. M1, few rich guys. Pentium. Okay, Ryzen. Good. i5, i7, i5 8th generation. Good, good. It's a good distribution. Now, what is the amount of memory that is there on your system? 32 GB, 256 GB, 8 GB, 256 GB, 512 GB. Okay. 16 GB RAM, 1 TB SSD. Okay, good, good. Nice. So you have a nice reading assignment by the end of today's lecture. So it's a fun reading lecture. So please do watch that. Okay, so yeah, remember any hardware, it has processor, it has memory, and it has bunch of IO devices. Thank you, everyone. And what is, so here is a kind of rough architecture or very, very high level architecture of your of a computing system. There is a processor, and the processor is connected to the memory. Your processor is connected to memory. This is your RAM, which you are seeing on the rightmost side through a memory controller, and there is some kind of bus which connects your CPU and your memory controller, and then there are a bunch of IO devices. And your memory, think of your memory as a linear array of bytes. It's a linear array of bytes. So this is byte 0. So this is byte 0. So this 0x0, 0x1, 0x2 that is written there on the side, it's in hexadecimal form. Okay, we will revisit hexadecimal form later, but this is simply put, no, let me use a different. So this is byte 0, this is byte 1, byte 2, byte 3, byte 4, byte 5, byte 6, so on and so forth. So your memory is a linear array of bytes. It's a linear array of bytes. And every byte, I really want you to understand this concept. These ideas are very important. And every byte, it is a collection of 8 bits. It's a collection of 8 bits. Byte means 8 bits. So like, for example, this is B0, B1, B2, B3, B4, B6, B7. It is a collection of 8 bits. And this is what is called as a least significant bit. Bit 0, it is called as least significant bit, also called as LSB. And bit 7, it is called as an MSB, most significant bit. So the bit on your right side, it is called as a least significant bit. And the bit on your left side, it is called as a most significant bit. And every bit here, it is realized using some hardware structure. Okay, every bit is realized using some hardware structure. And typically in the systems that we use, which are based on silicon-based systems, so every bit is realized using a transistor or one or more transistors. Every bit is stored using a hardware circuit consisting of transistors. Or there are other ways of some physical means of representing these bits will be there. All right. So can you tell me one simple hardware mechanism to store these bits? Do you have any ideas to, can you tell me some simple mechanisms to store these bits? MSB is always to the left. That's true. Yeah, light bulbs. a capacitor. So light bulbs, Ronak said light bulbs. You know, when you switch on a light, LED, let's say you can use 8 LEDs, and if a LED is up, then it means it's 1. If it is, if you don't supply power to it, it is 0. Or switches, a switch up means 1, down means 0. Or we can use capacitors, as Maharna is mentioning, like a charge on the capacitor is 1, a no charge on the capacitor is 0. Soham is talking about magnetic tape. Similarly, we can, there's a particular way of encoding bits on magnetic tapes too. Relay switch. So a fundamental idea in programming, in computer science or in engineering, is this idea of an abstraction. So when we say, hey, a byte consists of 8 bits, B0 to B7, B0 is the least significant bit and B7 is the most significant bit. And so that is the abstraction that is given to us. But how this abstraction is realized underneath, that is how each of these bits are represented in the hardware, is abstracted away from us. We don't need to worry about it. So most important idea is abstraction. So what is the abstraction that we are working on? So we are provided with this abstraction of a byte, and we say a byte is a collection of bits. This is the abstraction that is given to us. And how it is physically realized underneath, we don't need to bother about it. We don't need to worry about it. At least for the time being, we don't need to worry about it. On the, so from the byte, we construct this memory abstraction, that is, our memory is a linear array of bytes. That is, there's a 0th byte, first byte, second byte, third byte, so on and so forth. And that is the memory abstraction. So what is the, so we have the bit. So a bit is either a 0 or 1. And from bit, we construct a byte. And from byte, we construct our main memory or RAM. And here, how this bit is represented underneath, and all these things, we don't need to worry about it. So this is the abstraction that we need to keep in mind. Just want to check, you're all with me here. This idea of abstraction is very important, because we need to kind of leave certain details for our own benefit. We can revisit those details later. Abstraction, computer science is all about abstractions. How do we build very nice abstractions, and how do we use nice abstractions? No, it defines most of the work that we do. All right. Now, since we are here, so let me also, so what is, so when we have 1024 or 2 power 10, 2 power 10 bytes is equal to what? What do you call as 2 power 10 bytes? This nomenclature, it should be clear to you. 2 power 10 is 1 KB, 1 kilobyte. 1 kilobyte. And 2 power 10 KB is what? 2 power 10 KB is 1 megabyte. And what is 2 power 10 MB? 1 gigabyte. And what is 2 power 10 GB? 1 terabyte. So put it in another way for you to easily remember. So 2 power, so 1 kilobyte is 2 power 10 bytes. And 1 megabyte is 2 power 20 bytes. And 1 gigabyte is 2 power 30 bytes. And 1 terabyte is 2 power 40 bytes. All right. Good. These basic ideas, I know you may be knowing them before, so but I still want to emphasize so that for once we cover them clearly in the lecture and then they stay there with you all the time. So you'll have the clarity. Good. So your memory, if you see on the right hand side, there is it's a linear array of bytes. And another important idea I would like you to remember is, when the processor wants to, a byte is the least addressable entity. Like for example, so if you want to access, what I meant is, if you want to access, let's say, bit 4 of byte 6, it is the bit 4 doesn't have an address. So you need to fetch this whole byte. This whole byte you need to fetch into the memory. And from there, you will extract what this bit B4 is. This bit B4, it doesn't have an address by itself. It doesn't have an address or a name by itself. It is part of this byte 6. So whenever we want to access a particular bit here, you cannot directly, the CPU cannot directly say, hey, I want to access this bit. But instead, what it does is it fetches this whole byte 6, this whole byte 6 it fetches, and then it looks at the particular bit it is interested in. So the least addressable entity is byte. So you don't have an address beyond it. So there is this question, why do you think there are no addresses for each of these bits? Does it make sense to have an address for each of the bits? A bit wouldn't contain any information that makes sense. No, bit would contain an important information. Bit contains a valuable information. Every bit, so same bit, lot of addresses. Lot of addresses is the thing. Like for example, imagine if every room in your home has an address, how it will be? It will be bad, right? So every room in your home, if it has an address, then it doesn't make sense. So too many addresses. Every bit can store the address of next bit. Confusing. So let's see what is confusing. Every byte in your memory, it has a name. It has an address. This is byte 0, byte 1, byte 2, byte 3, byte 4. Just like houses in a colony have no house numbers, every byte in your memory, it has an address, a number. What we are saying is the bits within a byte doesn't have any address. You just have to access the whole byte. We'll revisit that idea, but broadly speaking, think of this, keep this analogy in mind. The bits in a byte are like the rooms within your house, and they don't have any separate address. The whole house has an address, but the rooms within the house doesn't have address. Are you fine with this analogy? Yeah, think of it that way. So in a colony, if your whole colony is, think of it as a memory bank, every house in the colony will have a number. Yes or no? Every house in the colony has a number. That is nothing but, every house is nothing but a byte. And the rooms within your house doesn't have address. The bits within a byte doesn't have address. Just keep that this much information, and then we will revisit this idea again later. There are some questions. As we progress, you will get more answers. I would not like to answer all these questions at the same time, because so again, so when you're trying to understand, one important idea, this idea of abstraction, you should use in your learning process also. How much you want to look into the details and how much you want to keep aside, so that we can proceed further. And at some point, we open the box and understand those ideas. Okay, so use that idea in your learning process also. Okay, so if you have some troubling questions, you can possibly keep them aside and just look at this view, that a byte is a collection of bits and memory is a linear array of bytes. And how does your processor, your computing system works? So here, if you see, so you have your memory, and yeah, you have your processor, you have your memory. The instructions of the program that you are executing, they will be present in the main memory of your system. Like for example, when you are running the Zoom software, the instructions in the Zoom program, they will be present in the main memory of your system. And if you go check, like you can see your Zoom program is occupying some 100 MB of your memory or 120 MB of your memory, something like that, you will get to know. Can you check and tell me how much memory your Zoom program is occupying, and put it in the chat box? Let's see. How do you see how much memory it is occupying? 350 MB, 322 MB, 216, 138. Yeah, task manager. You can use the task manager. And if you are using Linux, maybe you can use some other command, activity monitor in Mac. Around 250 to 300 MB seems to be system monitor in Linux. Huh? Okay, htop in Linux. You can use top in Linux. Good. I need more answers. Okay, it's fun exercise. So it is 150 statistics in Zoom setting. That's boring. Yeah. No, not boring. So that's also a good way to see. Around 300 MB, 250 MB. 250 MB looks like an average to me. Okay. So the instructions of your Zoom program, they are they are occupying around 350 MB of your memory. So let's say if you have 4 GB RAM, what percentage of memory is occupied by your Zoom program? What percentage in your system, what percentage of memory is occupied by the Zoom program? 7%, 2.7, 2.9. Of course, it depends on the amount of memory you have. Some students, some of you have 8 GB RAM, some of you have 16 GB, some of you have 32 GB. Great. Nice. Good. So it's fun exercise. So anyway, the instructions of your program, of your Zoom program, they are present in the memory. And what the processor does is, the processor is the one which does actual number crunching. Actual computations are done by the processor. It fetches the instructions from the memory. It decodes the instructions. That is, it tries to understand what is this instruction. Is it an add instruction, subtract instruction? There are varieties of instructions. It tries to understand what that instruction is. That is decoding the fetched instruction, and it executes that instruction, and it goes back and repeats the same. So that's what, so when you switch on the computer, this is what the processor does. The processor fetches an instruction from the memory. It decodes the fetched instruction, and it executes the fetched instruction. And it keeps on doing the same ad infinitum. All right, this is what is called as a fetch, decode, and execute cycle. So this is called as fetch, decode, execute cycle. And the cycle keeps continuing. Your processor does fetch, decode, execute, fetch, decode, execute, fetch, decode, execute. Are you all happy so far? Anyone who is feeling a bit lost, please put a message to me separately if you're not sure. Oh, there is an interesting question. So they are already twice from Balakumar that these instructions are stored in binary form in the RAM. Why should CPU decode the same? Good question. Like, for example, the instruction that is fetched, it is something like this. I'm just, this is a sequence of 8 bits. So maybe the first 4 bits, it looks at the first 4 bits, and 1011 means it could be an add instruction. Or there could be some other instruction like 1001 and 1100, and 1001, it means a subtract instruction. Decoding means the CPU looks at this bit pattern and try to associate what is the meaning of that bit pattern. Is that bit pattern corresponds to add, or is that bit pattern correspond to subtraction? And this is what is called as decoding logic within the processor. Good question. I don't want to go into further details, but Shivaya Jain has a very good question. So this keeps continuing. Your processor continuously keeps doing this unless you kind of switch off the processor or put the system in a sleep state. This cycle keeps on continuing. Sometimes it will be busy doing nothing. Okay, but it will be executing some instructions, but those instructions may not do any productive work at the end of the day. Again, very interesting question. How does it identify an instruction from data? Good, very good question. I'm not going to answer that question. Nice. So there are some nice questions. I'm holding those questions for the time being. For the time being, so let's say a processor has a way of separating, yeah, instructions and data. There's a magical way for it, to distinguish instructions and data. But this is what I want you to understand. First idea is the program that you are executing, the instructions of that program are present or in the main memory. And the processor fetches these instructions one at a time, decodes these instructions, that is, understands what the instruction that it has just fetched, and carries out the execution. All right. So far, so good. Till this point, there are some interesting questions. Please hold on to them. But apart from that, I hope you are doing all right. So more interesting questions coming, but we will kind of hold, we'll revisit those questions again sometime later. And this course is all about computer, this is computer programming. And your program is a sequence of instructions along with the necessary data. Okay, your program is a sequence of instructions. And yeah, so this program, when you execute the program, this program acts on some data. Like, for example, you could have written a program to convert a color image to a grayscale image. So the instructions of the program include, work on this data, process this data, this color image pixels, and transform these color image pixels into grayscale gray pixels. So the definition, a program is a sequence of instructions along with the necessary data. So your program is a sequence of instructions, and every instruction is a sequence of one or more bytes. And your data is a sequence of, is also a sequence of bytes. And every byte is a sequence of 8 bits. So overall, you can think that your program is a sequence of bits. Your program is a sequence of instructions and associated data. And every instruction is encoded using one or more bytes. And every byte is nothing but 8 bits. So you can look at your whole program as a sequence of bits. So when you download a program from internet like Chrome or even Zoom software, the program is transferred to your machine from that server as a sequence of bits. And your program is stored on the computer, on your system, also as a sequence of bits. So at the end of the day, when you are working with modern computing systems, finally everything is nothing but a sequence of bits. But we kind of store this sequence or encode things in such a way so that from this sequence of bits, we will be able to recover the whole story and the structure behind that bit stream. This is yet another important concept I would like you to understand. So later on you will see, so in your system, one important I/O device is your secondary storage structure, that is your hard disk. And there are two kinds of hard disks. One is called as, one is based on, what is this, magnetic disk technology, which is called as HDD. And other one is based on solid state technology, which is called as SSD, HDD and SSD. The primary property, so first question, the primary, before I ask that question, the primary property of this HDD or your hard, or secondary, this is also called as non-volatile storage or non-volatile storage or persistent storage. Persistent storage structure. This is also called as persistent storage structure or non-volatile storage structure. So the property of this is, even when you kind of remove power supply to your system, let's say on your laptop, even if the battery drains out, or on your desktop, even if you switch off your desktop, whatever data that is stored on your HDD or SSD, it still remains, so that when you boot, everything that you have written into the memory will still be there. But whereas whatever that is present in the RAM, so once you remove the power supply, it's gone. And when you reboot, all the contents of the memory is gone. So your RAM or main memory is volatile and your hard disk is non-volatile. So when you want to execute your program, the program that you would like to execute, like the Chrome web browser or Zoom, initially it is present on your hard disk. Like when you install your Zoom software, your Zoom, it is installed and it is there on your hard disk. Okay, let's use hard disk to mean either be it HDD or SSD. So this your Zoom software, the instructions of the Zoom software are present, of the Zoom program are present on HDD. And when you double click your Zoom icon or start your Zoom program somehow, then what happens is the instructions of the Zoom program are loaded from the hard disk into the RAM. So this RAM is also called as primary memory, and this one is also called as secondary. Okay, so the instructions of the program are loaded into the memory, and the processor starts executing the instructions that are loaded into the memory. Are you with me? So you give a program for execution. The instructions of the program are loaded from the hard disk into your memory, and these instructions are fetched one at a time and executed by the processor once they are loaded into the memory. So this is the most important idea that I would like you to remember, that if your program is residing on the hard disk, the processor doesn't care about it. It doesn't know anything about it. Only when you invoke a program for execution, then the instructions of the program are loaded from the hard disk to the RAM or main memory. And once the instructions are loaded into the main memory, the processor starts executing the instructions of that program. Are you all with me here, this idea? So there is this question, what does non-uniform access means? We will talk about it maybe in the next class. Today it is, it's 11. So we'll conclude today's lecture. One question. So some of you answered when I asked, what is the size of your memory? Some of you said 256 GB, 512 GB. So those, the 256 GB RAM you will not have. Usually the size of your main memory is 4 GB, 8 GB, 16 GB, 32 GB. That is the order. But the size of your hard disk secondary storage structure, it will be in the order of 512 GB, 256 GB, 1 terabyte, 1 TB. So, so here, yeah. So some of you got confused. So I want you to, I noticed it, but just kept quiet at that time. The size of your RAM, it's in the, it's something like, it will be in this range. Beyond the 16 GB on your laptops, it is usually not the case. But on server machines, you can have more than 32 GB. This one, it will be your hard disk, it will be 256 GB, 512 GB. So this is how it will be like 1 TB. So, okay. So what is the summary of today's lectures? We'll conclude. What are the important, what important ideas you learned? Can you just quickly put in the chat anything you knew you learned in today's lecture? You can put 1 or 2 words in the chat, and then we will conclude the today's lecture. Abstraction, bits and bytes, processor memory. Execution model, how memories. So there is this question, what does HDD hard disk or persistent means? When you write some data to it, it stays there even after the power supply is removed. Good. So next lecture, we will continue. So, and get these fundamentals all right. And perhaps we'll look at a small C program in the next lecture. And let me, there is a question, what is the course structure? How will we be graded? Shreyas, let's not worry about no, the grading immediately. So we will, we'll get back to you on that. Okay, so let me stop recording.